In the next session, we will discuss about acids and bases. To understand this, first we have to see the ionization reaction of water, which is also an equilibrium process producing an H plus aqueous and OH minus aqueous. We can write down the constant for this equilibrium, which is equal to K, and the K will be equal to H plus multiplied by OH minus. And in this case, we don't divide with H2O, as H2O is liquid and we only consider the aqueous and gas phase. And the K here we normally call as KW, and the W stands for the water because here we are talking about the reaction of water ionization. Now, the KW for water at the room temperature is 10 power to the minus 14th. And therefore, if we have the H plus being equal to the OH minus, the value is equal to 10 power to the minus 7th. And here we will be introduced to a different term, which is called the pH, and this is equal to minus log H plus. And minus log 10 power to the minus 7 is of course equal to 7. We also know the pOH, which is minus log OH minus, and in this case it will also be equal to 7. In general, the sum between pH and pOH will result in the value of 14. And this is the one that we call the neutral condition. So at neutral condition, the pH will be more or less equal to 7. For acids, the solutions will have the pH smaller than 7. And for bases, the solution will have the pH higher than 7. So in the acid system, the H plus will dominate, so will be bigger than OH minus. While for bases, the H plus will be smaller than the OH minus. In general, there are 3 definitions of acids and bases based on 3 different theories. The first one is from Arrhenius. And Arrhenius stated that acids is something that releases H plus to the solution, while bases are the ones that release OH minus. Now, Bronsted-Lowry expands this definition. The acid still releases H plus, but the bases do not necessarily have to release this OH minus, but they have to accept the release H plus. Even though they do not release any OH minus, they are still base as long as they accept H plus. And Lewis further expands this theory where it is stated that acids are the compounds that accept lone pair electrons, while bases are the compounds that donate lone pair electrons. So based on these 3 definitions, we can actually define which one are the acids and which one are the bases. But it is important to note that these theories, they do not contradict between one another, but rather one expands after one another. Per definition that we have discussed, we can take a look at this reaction between acetic acid and also ammonia in aqueous phase, and forming the acetate ion and ammonium ion. So therefore, it will become negatively charged after losing 1 H plus, while NH3 will be receiving that released H plus and become the NH4 plus. So per definition, CH3COOH donates their H plus, NH3 accepts that H plus, and therefore we can say that the CH3COOH is an acid and NH3 is a base. On the other hand, we can say that the CH3COO minus is a conjugate base because it was once from an acid, and NH4 plus is the conjugate acid because it came from the NH3. Now, this is what we call the acid-base conjugates, and it is important to note that the difference between acid and their conjugate base, as well as the difference between the base and their conjugate acid, is only 1 H plus. And the one with more H plus is the acid, and the one with less H plus is the base. So if you see a compound where you have more than one H plus difference, for instance H2CO3, which is carbonic acid, and CO3 2-, these are not conjugate pairs. Why is that? Because as you can see, the difference are 2H plus. H2CO3 lost 2H plus to become CO3 2-, so these are not conjugate pairs. The conjugate pairs, the difference between them is only 1H plus. Now, between H2CO3 and CO3 2-, we will have another molecule, which is the HCO3-. And H2CO3 is a conjugate pair with HCO3-, and HCO3- is also a conjugate pair of CO3 2-. Now, elements or compounds like this, where it can be both a base if you compare to H2CO3, but it can also be an acid if you compare this to CO3 2-, we call this an amphoteric compound.